Okay, so here we go. Kind of, this is part 2, but it's really going to be just part 1. So again, it's Friday, March the 14th. Advanced level chemistry here at Spain Park. So we just weighed our stuff. Obviously, it was a precipitate. Okay, what two things reacted?
Na2CO3.
Na2CO3. And what state did we just say that was? Aqueous. Plus CaCl2 aqueous. So we've already learned what type of reaction is this. Double replacement. Okay? Compound plus a compound. So they're just going to swap. So what's my positive thing here? What's my negative thing here? Say that again.
Na is positive.
Na is your positive. CO3 is your minus. Calcium's the positive. Cl is your minus. Okay? But it's an Na plus. We just have 2 of them. So what are we going to make?
NaCl.
NaCl, which is Na is plus and Cl is minus, plus CaCO3. Now we need to balance this.
2 on the NaCl.
Okay? 2 there. Now we have to go through the very difficult, challenging process of which one is the precipitate. Obviously, one of those was a precipitate. Now maybe both were. Okay? But what do we know? What is the name of NaCl?
Salt.
Salt. Table salt. Is that soluble in water?
Yes.
Yes. Have you ever swam in the Gulf? Do y'all have a saltwater possibly pool at your, in your neighborhood or at your house? Okay. Have you ever put salt into the water with cooking pasta noodles to try and make it taste better?
That doesn't work.
Okay. Have you ever had a saline solution for your contact lenses? Okay. All of that is salt, is aqueous. All right. I don't even know that. I don't exist in the world. I don't notice anything that goes on in the world around me in a common sense state. Okay. I don't know that there's salt in the Gulf. I don't know if my mom ever put salt, or dad, ever put salt into the pasta noodles. So I can look on that ion sheet right there, my solubility chart, and I look at the bottom and it says Na plus, K plus, and other cations of group 1, and it says there are no common anions in column 3 that form precipitates. Because as challenging as that solubility chart is, 1 plus 2 equals aqueous, 1 plus 3 equals solid. That's been a challenge all day long today. Okay? 1 plus 2. So if the thing's in column 1 and you combine it with something in column 2, that means it's soluble, it's going to be aqueous. If you take something in column 1 and combine it with anything in column 3, it's going to be a solid. So if I look at sodium, is there anything in column 3 that it's going to combine with to make a solid? No. Because what do we know about all alkali metal compounds? All alkali metal compounds are always soluble. All nitrates are always soluble. Okay? Hopefully there's common sense here that tells me that. So what's the state then of NaCl? Aqueous. So what must have been our white solid? The CaCO3. Okay? Now, the other classes had some severe issues with being able to change simple grams to moles and determine the limiting reactant. So we're going to practice that first before we get into the lab. So again, to determine our limiting reactant, here are our simple steps. You convert grams to moles, or whatever the quantitative information is, you always go to moles, and then we divide by the coefficient in front of that substance. Now in this one, what are our coefficients? 1 and 1, right? Everything's a 1. So now once you get your limiting reactant, we can determine the mass of the unknown. And for us, in our lab, what's the mass of the unknown going to be? What mass are we concerned about? Because isn't that what we just collected in the filter paper?
Yes.
So this would be my unknown mass. I need to know, and when I solve for that, is that gonna be my actual yield or my theoretical yield? What's my actual yield gonna be?
What we actually got.
What you just weighed, right? And then we can get our percent yield from that. So let's look at the sheet that I just gave to you. Let's look at question number 7, okay? Question number 7. Oop. Right there. That's good. Gonna try right there. And just for my information, I don't know if you recall, hopefully you do, when we were talking about composition reactions and learning and giving you examples of different types of synthesis or composition reaction, I talked about the acid rain cycle. That coal has sulfur in it. And then when the coal burns, the sulfur burns and produces sulfur dioxide as a pollutant. Goes up into the atmosphere, reacts with more oxygen, making sulfur trioxide, and then mixes with the water in the clouds, and it rains down sulfuric acid as acid rain. Okay? This is that pollution right there. Coal company, natural gas, power companies that burn coal now have to scrub the SO2. So this is the process that in those big smokestacks now, when you see the white smoke coming out of them, it's not pollution, it's going to be this, so they're scrubbing the SO2 out of the pollution, and it ends up making, this is actually a solid that then collects, and they actually, that's what they make gypsum or sheetrock out of. And they can use that and they sell it off, and it's actually recycling the technical pollution from that. And so that's just one of the reactions that they can use as an anti-pollution. So in the smokestacks you see now, they always kind of scrub and get that SO2 out of there. That's just, in my opinion, that's the interesting. That's what makes chemistry, that's what makes the world a safer, a better place through chemistry. Better living through chemistry, also with chocolate. So when I'm looking at this, I have, in a particular experiment, 255 grams of calcium carbonate was reacted, exposed to 135 grams of SO2. And some other things, but mainly those two things. In the presence of an excess amount of other chemicals required for the reaction. But we're only worried, we know the balanced equation is 1-to-1. So what's my theoretical yield of this? Well, what has to happen first? This is just like our lab now, except we use 2 grams and 2 grams, or approximately 2 grams and 2 grams, whatever data you use. We want to know the theoretical yield. So what do I have to do? To find what?
The mole ratio.
Okay, but which one do I use? I start with my given, but which one's my given? I know, but I got 2. I got 255 and I got 135.
You started with 255 of CaCO3.
Why?
So you can check how many moles that are there first. And then
Okay, what do we have to find? What does the limiting reactant do? Limits what? The reaction. It limits how much product can get made. Because one of them is going to run out before the other one. The first thing you got to do is figure out which one's going to run out first. Which one is the limiting reactant? Because when one of them runs out, no matter how much of the other one there is, the reaction is going to stop. I mean, we can make this very, very simple. I have very simple. Ooh, I thought that was blood. Okay. Come on. Get some air in there. All right, so I have a candle in a jar. Okay? I have the candle in the jar. When is the fire gonna go out?
The oxygen stays.
Now, if I didn't put a lid on it. When the wax runs out, because as long as the lid's off of it, there's plenty of oxygen, right? Oxygen's the excess reactant. The wax is the limiting reactant. But as you suspect, if I put the lid onto it now when is the fire going to go out? Okay, even though we got plenty of wax, plenty of candle, when the oxygen goes out, it's kind of like, is it Beauty and the Beast, or there's something where the candle goes out, some movie, Disney movie, the candle. Oh yeah, the something, that one. Okay, so now all the oxygen's gone, but we got plenty of wax. So when one of the reactants runs out, the reaction stops no matter how much of the other one. When the candle runs out, there's still plenty of oxygen in the air. When the lid's on it, now there's still plenty of wax, but the candle goes out. Now, so I have to find my limiting reactant. So how do we do that? Well, I got 2 easy steps right here. How do we do it?
Convert grams of substance to moles.
Convert grams of each substance to moles. So I'm going to say 255 grams of calcium carbonate. And somebody please tell me, how do I convert that to moles? Thank you very much. Molar mass. Somebody tell me, how do I calculate the molar mass?
Add them together.
Add them together. And this is what I've been fussing at everybody all day long. If you do not know how to calculate the molar mass by this point, you need to go home and do some serious review, because we've been doing this since chapter 3. Okay? You need to know how to do this. If you don't know how to calculate the molar mass by this point, you need to zone in and just not exist in the classroom. You need to actually start getting stuff sinking in. Okay? Because I can only go over something so many times, and then it's just blah 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 blah. Okay? So we need to make sure you know how to do that. So what is the molar mass?
68.9.
Try again. You got 3 oxygens. Okay? We've got to know how to calculate. This is not supposed to be something new.
I didn't put the times here.
Okay?
100.09
100.09. And where does grams need to go?
on the bottom.
Okay? Now, y'all, it's a lot of times you guys are just here and you're just writing these numbers down, and then you're just trusting where they came from, and then when it comes test time, you don't know how to get the number. Make sure you should know how to calculate this. So it's 1 mole over 100.09.
Yes.
And that turns out to equal how much? It's going to be right around 255.
2.55.
2.55, that's what I meant. 2.55 moles of CaCO3. So now we have to do the exact same thing with 135 grams of SO2. So what's the molar mass of SO2?
64.07.
Okay? Well, again, how do we get that? Well, you were looking out, I just saw, some of y'all, sulfur is 32.07. What we should have oxygen memorized by now. 16 times 2 is 32. So 32 and 32 is 64.07. Okay, so we divide that out, and this comes out to 2.11, I believe. Okay? That was sarcasm in my voice. What do we divide by each one? 1, so get your calculators out if need be. So we divide each one by 1, what do we get? All right, so which one obviously is my limiting reactant? SO2. Now, yes, is it 135 here and 135? No, it's 1 mole combines with 1 mole, but they have different molar masses, obviously. So we can't just say it's a gram to gram ratio. So you have to convert to moles. You divide by the coefficients to see if they're in the right ratio. Since it's 1 to 1, it's easy. So this is my limiting reactant. Okay? So, if I have that, now I'm always going to use the limiting reactant to determine everything else. Doesn't matter how much CaCO3 I have because not all of it's going to react. I always use the limiting reactant because it's the one that determines how much product gets made. Now we have two choices here. Some of y'all that understand the math, we've already done the mass to moles conversion. Some of y'all may need to just start back here. But now I want to solve, I need to get my theoretical yield using the limiting reactant. So I can come here, I can say 2.11 moles of SO2 times what? What's the next step in the process?
Moles unknown.
Over
Mole mass.
mole ratio. Mole ratio. Ratio is two numbers. It's always what I'm looking for over what's given. In this case, what am I looking for? I'm looking for my unknown, my theoretical yield. 1 mole CaCO3 for every 1 mole of SO2. Now if I stopped right there, what unit would I end up with? Moles of CaSO3. I'm right to here now, moles of unknown. So what do I need now? Of CaSO3. So again, 16 times 3 is 48, plus 32 is equal to 80, plus 40 is 120. If I add up the .0s, it's 120.15 grams over 1 mole. So all of that turns out to equal 3 sig figs, it's what? 254? And
253.
okay, so what does it come out? 253 point what?
5.
What exactly 0.5?
Yeah.
1.5.
Okay, so 254 then. Okay? So what is that mean? What does the 254 grams mean?
If you put in 135 grams of SO2, you get 250.
With plenty of calcium carbonate, more than enough calcium carbonate, you get,
254 grams.
you should get 254 grams if and only if everything goes perfectly. So what do we call that?
Theoretically.
That's my theoretical yield. Okay? So how do I get my percent yield then? If only 198 grams was actually collected,
198 divided by 250.
okay? So my percent yield, which is part B, is going to equal what you say, Nash?
0.78.
But what you say, Nash?
0.79.
But what? How do you get it?
198 divided by 250.
198, what you actually got, divided by what you theoretically maximum could get, and it turns out to be not 0.78, because percent you multiply by 100, so to 3 sig figs, it's going to be
79.2.
79.2. Do we all agree with that number?
Yes.
Wait, I got 0.779.
Oh wait, no, yeah.
So it would be 80%.
77.9 point, again,
Well, and then the next one is a 5, so it would round up to 80%.
I got
Put
70.
the
You gotta go to 77.5.
Oh, 78.
It's 0.781.
I read it wrong.
there's only one answer to this.
Sorry, I was
I got
Okay, y'all, you have a calculator in your hand.
I have it.
It's a simple division.
I read it.
77.95. So, but we want 77.95, but that's 4 sig figs. I only want 3. So the 5 rounds this 9 to a 10, which means it's a 0 and 78.0. Okay, it's like 3rd grade rounding here. Okay, 78.0%. Okay? Y'all? Advanced level chemistry, you ought to be able to do a simple division on a calculator.
I'm the master of the calc.
Okay? Now, so look, you convert to get your limiting reactant. You just convert to grams of each one. We need a mole ratio. So now I want us just to kind of look, and you're going to have to do, because we need more practice on this, but I'm going to help you all out here, and I'm going to do one more in the class here of your homework. And let's look at, I did 2 in the other class, but that one was too easy. Okay? So let's look at number 5. Number 5. So we have these reactants when they're heated together. So we got 20 grams of this one, and we have 10 grams of zinc. What mass of ZNO, X grams of this? Okay, and then we're going to add in B. Oh shoot, I forgot that in the C of the 7. B is how many grams of the excess reactant remain when the reaction is complete? Okay? So go ahead and see right now, can you determine which one is the limiting reactant and how much product we should get? Do this somewhere on, like, I would use a separate sheet of paper since there's not enough room really on that paper to do this. Rather than trying to cram it all in on margins and all that, sacrifice a piece of paper. Okay? And take a few minutes to do this. So go ahead and pause the video while we do this. Alright, so to convert each one to moles, the first thing we have to do is convert grams of each thing to moles. So we're going to use the molar mass. 1 mole over 65 point, I always say 65.4, but I think it's 3.8 grams. And then this one is 1 mole. What did we get? This is molybdenum. Some of y'all had to look at, find that one, probably search for a while. That's number 42. But what did we get for the molar mass of molybdenum? That would be molybdenum. I still said it wrong. Molybdenum 6. I said it, I had it in my head, and then I just got 6 oxide. What's the molar mass of this one? 140.9.
Yeah. 143.9.
Okay, that'll work just like that. That's close enough to government work. All right, so what do these numbers turn out to equal?
0.153 moles.
0.153 moles of zinc and 0.139 moles of the NO03. Okay, now that's nice, okay, but we can't just say because this one's less, it's the limiting reactant, because we need a 2 to 3 ratio. We need 1.5 times more zinc than we do of the molybdenum oxide. So I divide this one by 3, I divide this one by 2. So when I divide this by 3, I get 0.051. Divide this by 2, I get 0.0695. Okay? So which one is smaller?
Zinc.
The zinc. So this is my limiting reactant. All that's telling me is I don't have 1.5 times as much of this as I do this. Zinc's the limiting reactant. Okay? So I'm going to use that. Now, that's the one you use to determine the product. So I'm going to say, but I'm going to start with the moles. Do not start with that number. Start with the moles here. 0.153 moles of zinc. Do not start with the 0.005. Times, what's the mole ratio between the zinc and the zinc oxide? 3 to 3. 3 moles of ZNO for every 3 moles of zinc. Times, what's the molar mass of zinc oxide? 81.4 or 38 or, okay, 4. So what do we get? 12.46, 12.5 grams of zinc oxide is how much should be formed. That's my theoretical yield. Now, we only have 5 minutes left, but this 5 minutes is very important, so we need to zone in, lock in. Okay? Because the next question is, how many grams of the excess reactant? Well, I determined that this is my limiting reactant, which means that this one is my excess. So did all 20 grams get used? No. So there's some left over at the end, just like there's some candle left over in there when the oxygen ran out. How can I figure out how much MOO3, so mu, how much of that is left? Julie?
30 minus 12.5.
No. Okay? Because that's how much of this, but we don't know how much of this. It's not, because you have to figure in the law of conservation of mass. You got to figure in that part too.
You do 30 minus everything on the right side.
Yeah, but we don't want to go figure all that. I mean, you could do that. You already know this one. You already know 12.5. Okay? And then you could calculate this one, and then we would know this one, add them together, whatever, but there's a simpler way. Adarsh.
0.0. Wait, we're trying to find.
I need to know how much of this.
Oh wait, yeah.
Go ahead.
0.051 times 2. Right?
And that's good, but that would be in moles, not grams.
Yeah. And then you can convert it.
Okay. Here's the deal, since we're out of time. If you want to know how much is left over, the first thing you got to find out is how much got used. How much got used? So all we do is just make this my unknown now. Y grams of that. So we're going to start and do the exact same thing. Always start with the limiting reactant for 0.153 moles of zinc. Now what's the mole ratio between the zinc and the mu? Okay, but it's going to be 2 moles of MOO3 for every 3 moles of zinc. And then I need to go to grams. I already know the molar mass. It's 143.9 grams over 1 mole. So what does that turn out to equal? I'm just figuring out how much got used. Somebody on the calculator, quick, we're out of time. 2 or 3 people, since we have trouble with calculator.
14.6778.
14.67, so 14.7.
Yeah.
Okay, so what is that? That's how much we got what?
The excess.
No, that is not the
That's how much
excess.
got used.
That's how much got used. So how do I find the excess?
I want to hear how you subtract 20 minus that.
20 minus the 14.7, which is going to be 5.3 grams excess. So it's always going to be the given minus the used. So you just define the excess, you strictly find how much got used, making it just doing stoichiometry just like always, and then subtract what got used from how much was given. If you end up finding out more was used than what was given, then maybe you did your limiting reactant wrong. Okay, 'cause you can't use more than what you were given. All right, so the only thing different is we just make this one my unknown. The excess makes the unknown. Do everything the same. that tells me how much got used, subtracted from my given, that gives me my excess. Okay? Y'all, your homework for the weekend, okay? You have to do 1 through 7. Okay, you already did 7 and you already did 5. So it just means there's like, if my math is right, it gives you 5 left. Okay? Don't normally give homework over the weekend, but we're having a test on Tuesday and you guys obviously need more practice. The lab will be due, we'll talk about that on Monday because we just need to figure out how to do this so you can do the lab right. But you should be able to do all the calculations on the lab now.
Love to what?
Okay, y'all have a good weekend and go Jags.